Okay, so here's another problem. In this case, we want to find the displacement at D, which is the free end displacement. So again, let's talk about the techniques we've had so far. So with direct integration, could I do this with direct integration? Can I write a moment equation that's valid for the entire length of the beam? No. And the reason is this little applied load right there is going to mess you up. So again, you have to break into two sections. And an additional feature is that over the first 12 feet, the structure has a value of 2I, and over the last 8 feet, only I. Remember, direct integration, you're integrating the moment divided by EI. So even if this load were gone, you'd have to do one integration divided by 2I, and then another integration divided by I. And you'd have to add those together. It'd be kind of tricky. What about conjugate beam? Well, what kind of moment are you going to get with this uniform load? You're going to get a parabolic moment, and that's going to be a real mess to try to do, finding areas and centroids of, especially with this little applied load. Plus, you're going to have to divide by EI, and again, you're going to have a discontinuity here between the two. So we're only left with one thing, and that's the thing we're talking about right now. So we're going to use virtual work to see if we can solve this problem. So looking at the real system, how many equations for moment do I have to write? Well, the equation for moment doesn't have anything to do with I. So I'll have to write one from 0 to 6, and then a second one from 6 to, 20. Right? And the reason I'm having to do that is because of the discontinuity right here in that load.
Is there a hinge at C?
No, that's just a little, like a welded section to show you that the beam steps down to a different size. So there's a deeper beam here from A to C, and then welded on is a shallower beam. That's why the moment, the modular elasticity, the moment of inertia goes down. Okay, so in order to write these equations, I am going to need the reactions. So let's start with that. So I'm going to assume I have a reaction up here at A, call AY, and a moment here. I'll call it the moment at A. I know find those things to get started. Also, to help me get started, I'm going to take this concentrated equivalent, this uniform distributed load and find a concentrated equivalent value. So it's 1.2 kips per foot times, it looks like 20 feet. So that's 24 kips. Is that right? So it'll be 24 kips acting right in the middle. So that would be 10 feet from either side. So with that information, I'm going to slide over here to the side and find my reaction. So again, summing moments. Using right-hand rule, I'm going to sum moments at A and make sure I'm in equilibrium. So summing moments at A, I have the applied moment, which is negative. About A, these two forces also create negative moment. The first one would be a 6-kip force at a distance of 6 feet. And then my concentrated equivalent force, 24 kips. And that's going to be at 10 feet. So it looks like the moment at A is going to be negative. That's 240 plus 36 is 276. That sound right? Anybody else get that with the calculator? So 276, and that's going to be kip feet. So I know my beginning moment. And then I'll sum forces. I'll assume up for positive. And I'll make sure that when I sum those in equilibrium that it's 0. So I've got my reaction force up, AY, and then I have my 6 kip force down, and then the concentrated equivalent force is also down. So it looks like AY. Sorry? Question? Did I do something wrong? No? So 30. So let's come over here and look at the real loads. And when I do that, I'm going to have in a moment equation that's good from 0 to 6, and a second that's good from 6 to 20. So let's do the 0. Yeah.
I was going to ask, I'm sure you explained it, but just if you could one more time, how do you decide where you do cut it at again, where you decide to make your cut?
You mean how I break the moment into 2 segments?
Yes, so how you're saying, you're going to do from 0 to 6. And
well, that's because there's an applied load there. We know that what's going to happen to the moment when you go under an applied load.
So that's going to be...
It's going to change direction. Right? Because remember, the shear changes, and the change in shear tells you how the moment's going to behave. So I have a continuous curve here. I'm going to hit that point, and it's going to change slope. It's going to change direction. So that's a different equation. If that 6 wasn't there, I could write one equation because the load's constant, continuous, which means the shear would be continuous, which means the moment would be continuous. But because this load here, that means the shear is discontinuous. If the shear is discontinuous, then the moment is discontinuous. So let's do that. If I cut the structure here, I think it's going to be easier to work the left side than the right side. So I'm going to draw the free body diagram for that. So here's the beam cut at a distance x. And I know on the right side I've got my reaction force of 30 kips. And I've got a moment of 276 kip feet. And then, of course, I've got the distributed load, which I'm going to turn into a concentrated equivalent that acts through the centroid. So what is that equivalent force? What's a rectangle? So it's going to be base, which is x, times height, which is 1.2. So this will be 1.2x. And then all I'm interested at the cut is the moment. I'm not going to worry about the shear right now. So I'm going to sum moments, the cut, and let's see what I get. So I have my internal moment, that's positive. I have the moment due to the concentrated equivalent, which is also positive. That's 1.2x is the force. And what's the distance to the centroid? Half the distance? Be x over 2. And then I've got this 30 kip force, which creates negative with a moment arm of x. And then I have the force at the very end, which with this sign convention is positive. So when I solve for the moment as a function of x, what do I get? Well, I get something that looks like this. I can tidy that up. That becomes 0.6x squared. That's negative. Plus 30x minus 276. And that would be with units kip feet. Now the only thing I can check with this equation right now is I know the moment at x equals 0, or A, has to be equal to negative 276. And if you put in x equals 0, you do in fact hit negative 276. Oh, I forgot. Yeah, this is only good from 0 to 6. Let me put that in there so you can see that. So we're going to do it again for 6 to 20. So now I'm cutting the structure somewhere here, and you can look at the left side or the right side. And I think the right side's a little bit easier. You can go either way, but I'm going to go with the right side. So when I do that, you get something like this. So here's the distance x. That leaves my segment that I'm working on would be 20 minus x. And on that free end segment, I have my distributed load again, which is 1.2 kips per foot. So I know that the concentrated equivalent force there is going to be base times height. So that's going to be 1.2 times 20 minus x. Kind of squeezed it in there, sorry. And then at the cut, there's my positive bending moment. I don't think I'm going to leave myself enough room to solve this problem, am I? Oh well, get another piece of paper. So now I'll sum moments about the cut, make sure I'm in equilibrium. So the moment about this cut, so I've got the internal moment, which with my sign convention is negative. The concentrated equivalent force also creates negative moments. So the force is 1.2 times 20 minus x. And then what's the moment arm to the center? Well, it's the distance divided by 2. So that's going to be 1/2 20 minus x. Oops. 20 minus x. That's it. So it looks like the moment x here, move that to the side of the equation, that 1/2 will take that out, so I get minus 0.6 20 minus x squared. Well, how can I check that? Well, from 6 to 20, I know the moment where? The free end. What is the free end moment? 0. That's at x equal 20. I put in x equal 20, I get 0. What else do I know? At x equals 6, the moment from the first section should match the moment from the second section. So put in x equals 6 and see what you get. I can't do that calculation off the top of my head. That would be 14 squared times 0.6 for the bottom, and then you guys can do that. So see if that, in effect, checks. Plug in 6 in each one of them. This is the easiest one to do. It would be 14 squared times 0.6. I don't know what that is. It's negative, I know that.
Negative 117.6 for both of them.
Oh, you got them both? Okay, cool. So I'm going to go ahead and put little green check marks there. I think both those are in good shape. So what do I do next? Got my real moments. Now I need my virtual moment. So see if I can squeeze this down here in the bottom. So let's do my virtual system. What does my virtual system look like? Well, I have a fixed connection, and here's the geometry of my beam. Where does my virtual load go? Well, the problem says I want the displacement at D, so I put a virtual load at D. And I'm going to assume that that load acts down. So there's my problem. How many moment equations do I need for this system? 1. And I don't even have to find the reactions. Because if I cut it, you want to work the right side or the left side? Well, I pointed right. Left side, right side. Ooh, I would work the right side. I don't have to do any work. I don't have to find any reactions. I can go right to that equation. So this will be an equation that's good from 0 to 20. So my free body diagram looks something like this. Over to the cut, a distance x. That leaves me a remaining segment of the length 20 minus x. I have my virtual load at the end, value of 1. And then internally, I have my positive virtual moment. So if I sum moments at the cut, make sure it's in equilibrium, what do I have? Well, I have my internal moment. Is that positive or negative? That is negative. And then about the cut surface, the virtual load also creates negative moment. The force is 1. The distance is 20 minus x. So my virtual moment is equal to, if you run the minus sign through, you'll get x minus 20.
Okay.
Yeah.
If you're doing your range 0 to 20, why are we breaking it up between x and 20 minus x?
X and 20 minus x. This is, I'm cutting it at x, but I work the right side, not the left side. Right? I'm cutting it at some distance x. You can work the left free body or the right free body. I chose the right free body.
Okay.
If I choose the left free body, which you can, you have to find the shear and the moment over here. That takes 2 equations. When I go this one, I don't have to find anything. That's what. And then, of course, when I cut it at some distance x here, I'm left with a segment that's 20 minus x. So there we go. The hard work is done. So all I have to do for my virtual work equation is to match these things. I've run out of paper. Let's see if I can find some. Anybody have a piece of white paper I can borrow? Copy paper would be nice. If not, can I squeeze it in? Maybe I can squeeze it in right here. Think I can squeeze it in there? Yeah, I think I can. Oh, you have a piece, Mr. Ryan? Oh, Mr. Patel has one. Thank you. I'll repair or replace it. Okay. So we can now write the displacement at C, which is normally, D, which would normally be defined as the integral from 0 to 20 of the real moment, the virtual moment, divided by EI, dx. But we know from our work over here that the real system is not valid from 0 to 20. I have one equation from 0 to 6 and a second from 6 to 20. And then down here we found the virtual one was good for the whole list, the whole length. So this is going to end up being, I'm going to take the 1 over EI out just to save me a little work. So it's going to turn into an integral from 0 to 6. So the real moment from 0 to 6 is all this stuff. Minus 0.6 x squared plus 30x minus 276. That's the real moment. And the virtual moment is x minus 20.
Would you divide all that by 2?
Why would I divide it all by 2?
2i.
Oh, I forgot. So I need to make this 2i.
Okay.
Right? Because it's the I is 2i. And then plus, the second one will be 1. Oh, that's good. That's a good point. Now when I go from 6 to 20, my equations match, but the I doesn't. So that means my next one will be again divided by 1 over 2 EI. and this will be an integral from 6 to 12. My real moment changes to this, minus 0.6 times 20 minus x squared. The virtual moment stays the same, x minus 20 dx. Now what changes in the next segment from 12 to 20, the integrand stays the same, but this becomes I. So plus 1 over EI, and the integral is from 12 to 20. I think you can see why I stopped asking you to actually do all the integrations and just write this equation being good enough, because you can get to this point, and doing all this multiplication and all that integration with multiple limit evaluations, that takes a long time. And it's just really at this point, I know you could do it without the pressure of the exam over your head. This is good enough for me. So what I'll want to do here is just circle these denominators to let you know the difference. So you can see from 0 to 12, I'm dividing by 2EI, and then from 12 to 20, I'm dividing by EI. These integrands are the same, but one is divided by 2 and one is not. So any questions about that? Okay.